Now we'll see the working of octave rectifier. The schematic of the octave rectifier is we have the screen. So we have a source which is now defined as a V sine. To define a sine source, so we are supposed to select a voltage source. So we need to edit some of the elements here. So you have to select the sine. So the parameters to be edited are the DC offset voltage 0. We have considered the input amplitude as 10 volt peak. The frequency of the signal is 50 Hz. So there is no delay, there is no phase shift, there is no degree, and we have assumed there are 10 cycles coming from this source. So let us select this, and since we are supposed to do a transient analysis with a frequency as 50 Hz, one cycle with 50 Hz corresponds to 20 milliseconds. So we have selected dot tran. So let us see what does this dot tran mean. Go to this simulate and then edit simulation command. Here you can see we have selected stop time as 40 millisecond and time to start saving data is 0 second and maximum time step is 0.1 millisecond. So with these settings, we're going to see minimum of 2 cycles because each cycle corresponds to 20 milliseconds. So we have named the input port as IP, the output as OP. So let me run this. Upon running, so we'll have this window. Let me see the input as well as the output over here. So to properly see the output waveform, let me see only the output waveform. As you can see, the green one indicates the input waveform, the blue is the output. For better clarity, let me change the color of output to red so that we can clearly see the waveform. So let me see uh, the working of this circuit. So as you can see here, so during fast half cycle output is almost following the input voltage, during negative half cycle output voltage 0. So let us measure the voltages over here. So let me just have two cursors, one on the input, one on the output. As you can see here, cursor 1 is on input, the cursor 2 is on output. So during the positive half cycle, the peak voltage is 10 millivolt as we can see here. So this is input 9.98, which is almost at the peak. The corresponding output voltage at the same time happens to be. So see here, this is almost a difference of vertical difference of microsecond, meaning that it's almost the same. It's overlapping here. So as you can see now, is almost 0, meaning that horizontally they are at same time. You can see there is a difference of vertical difference which is 712.862 millivolts. So this happens to be the diode drop. So this is your VD on what we are talking about. So during negative half cycle output voltage 0. So let me track the output voltage during negative half cycle. You can see now this is the negative half cycle. The output voltage is almost 0. As you can see now, this is the second cursor corresponds to output having an voltage of minus 9 nanovolts. It's almost equal to 0. So let us also see how does the current is flowing in this circuit. So to have a current also on the plot, uh, let me see the direction of current over here. So let me consider this. Now this is the current to the resistor R1, which happens to be same to the diode also. As you can see now, so let me just put the current in a different plot. For that, we'll go to this add plot. You can add a plot. Let me put the I of R1 on the other plot. See now, so the current is 0. So let me just place the cursor on IR1. You can see here the IR1 where the current is minus 9.6 picoampere, meaning that the current is 0. So pico corresponds to minus 12, so which is the reverse saturation current, which is almost 0 current. Now, during positive half cycle, the current is in terms of milliamperes. The current is in terms of milliamperes. You can see now the peak current is almost 9.26 milliamperes. So I want you all to verify how you are getting this 9.26 milliamperes, because what you have is, so during the positive half cycle peak, this is 10 volt. 10 minus the VDON is around 0.76 divided by 1K, happens to be around 9.26 milliamperes. So this way we can see both the current as well as the output voltage across the load resistor. So this is the indication of a rectification. So you have applied a sine wave, you are getting a half wave rectified signal. Now we can certainly verify these whatever output voltage you are getting over here. So suppose if I change the output resistance, does the output voltage vary or not? So for that, so I cannot have a simulation with 1K, 2K, 500 ohm separately. I can change the value of this resistance during the simulation itself. For that, so we have to use a different setup. So you have to select this resistor which you want to vary it. So instead of specifying a single value, let us pass a parameter within flower bracket. So let me name it as RVAR. So it's like a R variable resistor. Instead of a particular value, I'm just putting it as a parameter RVR. If I want to vary this RVR across some minimum and maximum values, let me select this spice directive, where I can specify dot op command. So this is dot step. It's a parameter you are varying. Dot step param. The parameter you are varying is RVAR. Now you have to specify the start value, end value, and the increment. So this statement will make this value of resistor R1 varying from 1K to 10K in steps of 1K. Now to understand the syntax of this one, so we can certainly go to this help and then help about the topics. Here you can type it as step function. You get the parameter sweep here, dot step. Click on this. Here you can see there are examples given here. So I have selected an example over here like this. So there are different types of examples that are given. So here you have dot step param R load list 5, 10, 15, and you can see there is one more parameter where you have, so this is dot step temp minus 15, 125, 10. So we are using a particular parameter. No, this is a parameter what you are trying to change. So you're varying the value of R load in this particular statement. So there is a list default value, or the name is given here. The list corresponds to, so it will be varying from 5, 10, 15. The thing what you have specified here is, so the one what we are using now in this particular case of param is, you are specifying an initial value, which is like over here in this example, dot step temp minus 55, 125, 10 means. So temperature is a parameter you are varying from minus 55 degree to 125 degree with an increment of 10. So as you can see here, step the temperature from minus 55 degree to 125 degrees in 10 degree step. So in our example, so what we have done is, we have specified a parameter by name RVAR with the initial value 1K going up to 10K in steps of 1 kilo. So let me run this again now. If I run it, okay, what I'll do is for the time being, let me see only the, so let me see only this output voltage. As you can see, since A half-wave rectifier, the output voltage is given by Vm minus Vd on by phi, where there is no resistor coming into picture. So the output voltage is independent of resistance, meaning the output voltage is a single value. So output voltage is not changing from its value. You can see it's always at same value, so you don't have different plots here. So let me just zoom this and find out whether we have any different values. So it's almost the same thing. So as you can see here, so they're just almost this is different 10 waveforms. So this is for one value of resistance, this for other value, but you can make out the output voltage is fairly constant at around 9.28 to 9.3. This indicates the output voltage of a rectifier is independent of the load resistance. Then what is actually varying when you change your R value? So let us see, add one more plane and let me see the current over here. You can add a trace corresponding to I of R1. See now. So you can see current through the resistors keep changing, because as the resistance changes, since the voltage is remaining constant for a given resistance, the current has to vary. So we can certainly make out different values of resistance, because if you can use this shift key, you can see now. So let me just take only. Now if you just use this arrow key, so is this cursor moving now? See now, this is changing from, so this is for the least value of, suppose we change this from, so let me just delete this. We have only one cursor. Let me have the cursor on this side. I'm just moving the second cursor, so let me move it here. Now this is the maximum current of 9.28 milliampere when the resistance is the least. Now you change this. Now you can see the current has reduced to 4.6. Now the corresponding value of resistance is now 2K. If the resistance increase, the current naturally reduces. Now you can see for different values of resistance, you have different currents. So this is what is the indication of the variation of resistance is causing to the circuit. The current is keep changing. After seeing that variation of resistance, let us go and try to find out how to do that filtering. So let me comment this. For commenting, you can simply write type colon there. There's a semicolon written, so this will get commented. So let me just go back and just make it 1K now. So it's now 1K registered. Now I'm using the fixed value of resistance. For filter, all of you know that you're supposed to put a capacitor here. I'm just putting a capacitor now. So let me make this connection. So you have this coming down here. So this is, now let me connect this. So let me change this value. Let me make it around 50 microfarad. So micro is U. Fine. Now let me run this program. If I run this program, now it is a 1K resistance and 50 microfarad capacitance. On running, let me see the input and the output. See now, the capacitor is because output voltage corresponds to voltage across the capacitor, so it is keep increasing. So as the input voltage is increasing from 0, it went to peak of when the input is 10 millivolt, the output is 9.26, because the difference of 760 millivolt is the VD on. So now the input voltage is reducing, but the output voltage is gradually reducing. So this is, you can see now this is keep reducing slowly, and once it comes over here, it again increases. So this we call it as a ripple in your output voltage. So let us also see how does the current changes.